So the reactions in chapter 14 that I cover here in this lecture, these are the reactions that I want you to know. There's some other reactions in the textbook, but we're skipping some of those, and we're doing just the reactions that are the most important in this chapter that I carry on to next semester too. All right, so the first is acid-promoted cleavage of ethers. So this reaction is pretty straightforward. We're going to have here something like diethyl ether, and we can add an acid like hydrobromic acid. So if you have hydrobromic acid in the presence of a lone pair bearing atom like a nucleophile here, then you might guess that something like this occurs. Well, then our next intermediate will be this protonated ether. Now we've kicked off bromide. So bromide now can come over and it can attack really either side here. So it's going to come over and let's grab a hold of that carbon and let's do this. All right, so one of those products is going to be ethyl bromide, and then this here, that's your leaving group. So you're going to have an alcohol. So plus, in this case, ethanol. Now ethanol is not safe. It's in the presence of this acid. So we can protonate that oxygen again and do another nucleophilic substitution. So here we have another HBr, and we can carry out that reaction. That'll give us this, which can then undergo another substitution reaction where we do that. So in the end, we end up getting this guy plus that guy. So they're here because the initial ether is symmetrical, we just get these two products. Now, they happen to be the same. If the sides were different, you'd get different products. Now, there's one little thing to watch out for, and that's phenols. So let's take a look at how phenols are involved and why we have to be cautious of phenols. So phenols are alcohols that have a benzene ring attached to the OH. So let's take a look at how we might deal with a situation like this. So let's start off with this, right? And then the same reaction can occur. So first step here, if you guys take a second and think about it, what's going to happen? Well, it's the same thing, right? So we're going to do this. Right, so here's what it's going to give us. It's going to give us this protonated ether. And then the next step of this thing here, we have bromide. And if you remember up above, I said, well, bromide can attack either side of that ether. So it turns out that that's true most of the time, but this carbon right here, let's just make a little note about that guy down here. So that is an sp2 hybridized atom. And these atoms cannot undergo SN2 type reactions. So this can't react via that substitution reaction. And specifically, these are following like an SN2 type of a reaction. That doesn't mean that reactions can't take place on carbons in a benzene ring. They just take place through other routes. That's what 2 chapters are dedicated to this next semester. So all we need to know now is that this fellow cannot undergo substitution. So because of that, we're going to come over here, grab a hold of that carbon, and we're going to do this. So what that's going to give us is CH3 Br. Right? And then we're also going to get here plus our benzene with an OH. And again, just to point out, this thing is phenol. And the other thing is that there's no further reaction here. So no further reaction can take place. So you're stuck, in this case, with the OH there. You can't replace that with a Br group. So that's what we end up with. All right. So let's take a look here at our next reaction. And this one is interesting for a couple of reasons. It's an interesting reaction, and it's also something that you have to watch out for in lab. So it turns out that in the presence of atmospheric oxygen, ethers slowly oxidize to form hydroperoxides and dialkyl peroxides. Now, the problem in lab is that these are highly explosive. That's not a good thing. So there are some precautions that we can use in lab to avoid this reaction. And one is we do not distill ether down to dryness. And the other thing is that we store in full bottles with tight caps. And in lab, we actually, occasionally we have a timeline for doing this, but we check for the formation of peroxides. And sometimes in the ether, chemicals have been added to inhibit peroxide formation. All right, so the reaction down here I just want to show to you. So here we have diethyl ether, right? And just being exposed to atmospheric oxygen, so excess means that you have a lot of it, right? What you end up forming is this, right? And that group right there is a peroxide. And because both sides here are alkyl groups, it's called a dialkyl peroxide. And the thing that you have to watch out for here is that these things can explode. So anyway, in lab, we just are careful to make sure that we're watching out for distilling to dryness, and stockroom folks and I are making sure to give you ether that's safe to use.